Right, this is Chapter 5, Quadratics, Complex Numbers. So we're introducing a new imaginary unit I. It's defined as the property that I squared is equal to -1. Therefore, the square root of -1 has to be I. So those two go hand in hand. What you see in this table is just a bunch of crazy stuff, but you're going to want to refer to it when you're doing the below examples. So it's telling you, and I think the most important side is this left side. You really don't need the right side. If we look at our first example, we have I to the 11th power. We want to narrow it down to I to the first, second, third, or fourth, like that left column. So what we need to do is we need to find the closest multiple of 4 that's in that exponent. So what is the closest multiple of 4 that is less than 11? So in our first case, it's going to be I to the 8th. But we still have to make sure it's equal to I to the 11th, so because of our exponent rules, we're going to multiply by I to the 3rd, because multiplication says we add our exponents. Anytime we have I to a multiple of 4, we can pretend it's not there, and we're just going to cross it out. I'm left with I to the 3rd. Now I can refer to my table above, where it says I to the 3rd is equal to -I. And then that's where it's simplified. So the simplified version of I to the 11th is -I. Next, let's look at I to the 65th. 64 is the largest multiple of 4 that is less than 65. So what do we have left? I to the 1st power. We can cancel and cross out that multiple of 4, and we're just left with I. I to the 88th power. That already is a multiple of 4. So we can cross it out, and anytime we cancel it out, it will be equal to 1. And that's like that bottom example where we have I to the 4th is equal to 1. Our last example, I to the 20, is the lowest multiple of, the highest multiple of 4 that goes into 22 without exceeding it. And then so we have 2 i's left over, I squared. Cross out the I with the multiple of 4, and let's look at our table. I squared is equal to -1. Next, we're going to simplify square roots of negative numbers. So it's going to be just like what we did in topic 3, where we found the biggest perfect square that goes into that square root and the other factor. But instead of breaking it up into 2 factors, we're going to break it up into 3 things. One is the biggest perfect square that goes into that number. So 16 is the biggest perfect square that goes into 48. Then we also have the factor of -1 because the number is negative. 16 times -1 is -16, so to get to -48 we need the square root of 3. We can simplify those first two. The square root of 16 is 4. We now know that the square root of -1 is I, and then the square root of 3 cannot be simplified. There's our final answer. Let's look at that next one. -63. The largest perfect square that goes into 63 is 9. -1, since the number is negative, and then 9 times 7. So let's simplify those first 2 roots. The square root of 9 is 3, the square root of -1 is I, and the square root of 7 cannot be simplified any further. Next thing we're going to look at is products of pure imaginary numbers. So what we have to remember is we multiply the coefficients as one thing and then multiply the i's as the other. So if we look at that first example, the first thing that I'm going to do is multiply -3 times 4 to get -12. Then I'm going to multiply my i's together. I to the 1st times I to the 1st is going to give me I to the 2nd power. We do know that I to the 2nd power is -1. So we're going to simplify that. -12 times -1, +12. Next example, right below it, we're going to multiply our coefficients. 3 times -2 is -6, times 5 is -30. I times I will be I to the 3rd power. So we can break that up as -30 times I squared times I, or we could have looked at our table from before. I squared is -1, and then we're left over with I. So -30 times -1 is +30, and the I cannot be simplified any further. When we're multiplying with square roots, we can multiply what's underneath and keep it underneath. So I can actually multiply -3 times -15 to get +45. This is just like a topic 3 problem. 9 is the biggest perfect square, and 5 is the other factor. Simplify the square root of 9 to get 3 root 5. Adding and subtracting complex numbers. This is just like adding and subtracting polynomials. You add and subtract the real parts, and then you add and subtract the imaginary parts. So only the coefficients are going to change. Let's look at that first one. 6 and 4 add to 10. Then we have I and -5i. I is like a positive 1i, so I have positive 1, negative 5. That makes a negative 4. Keep the I. The I does not change with addition and subtraction, just like when we add and subtract polynomials. Second example, we have to remember that the negative needs to be distributed to everything after it. So negative distributes to the 6 and the negative 2i, giving us minus 6i, or 6 plus 2i. Now let's combine like terms just like we did in the example on the left. 8 and negative 6 combine to 2. 3i plus 2i, add our coefficients to get 5, keep the I. Just like variables, adding and subtracting only changes the coefficients. Multiplying and dividing complex numbers. So we do need to FOIL. You can use the box method or FOIL. I'm going to use FOIL. So I'm going to multiply my first two terms, 2 times negative 4, negative 8. My outer terms, 2 times 2i gives me 4i. Inner terms, negative 5 times negative 4 is positive 20, keep the I. And then last, negative 5 times positive 2 is negative 10, but then I have I times I, which is I squared. I need to simplify and combine what I can, so those middle two terms, 4i and 20i, can be combined. Also, I know I squared is equal to negative 1. So I have negative 8 plus 24i. I have negative 10 now times negative 1, because I can substitute that in for I squared. So I have negative 8 plus 24i. Negative 10 times negative 1 is positive 10. And there's another set of like terms. Negative 8 and positive 10 combined to positive 2. 24i stays. Let's try it again with that second example. First terms, multiply to 9. Outer terms, multiply to negative 12i. Inner terms, add to positive 12i. So we can already see that those are going to cancel each other out. Last, 4 times negative 4 is negative 16, and I times I is I squared. So the middle terms cancel out, and we do need to substitute in negative 1 for I squared. So 9, and then negative 16 times negative 1, order of operations, I need to multiply first, is positive 16, add to 25. So we end up getting a real whole number and no imaginary numbers in our final answer. Last but not least, and we're going to do a lot more practice with this in class, dividing complex numbers. Just like you can't have a square root sign in the denominator, you can't have an imaginary sign in the denominator. So we're going to multiply by the complex conjugate, which all you're doing is changing the sign in the denominator. So in this example, instead of 2 plus 3i, we're going to multiply by 2 minus 3i. And because we can't change the value, we got to multiply by that over itself, so it's the same as multiplying by 1. And from here, we've got to FOIL both the numerator and denominator. So I'm just going to go through that because we already did FOIL on the last page. And it ends up happening that multiplying by the complex conjugate is going to cancel out the middle two terms in the denominator. So let's simplify the numerator, substitute in negative 1 for I squared. And then the two middle terms in the denominator cancel out, substitute in a negative 1 for I squared in the bottom as well. So we get 6 and then a negative 3 combined to positive 3 minus 11i. Negative 9 times negative 1 is positive 9, plus 4 gives us 13. And that's as far as we can go. I know this seems a little overwhelming, but this is just a preview. We're going to focus a lot more of it in class, so you will get any clarifying questions answered.